500 winters without cracks, and 30 years until complete destruction. Why do modern walls have such a short lifespan, while ancient buildings stand for centuries? We are used to thinking that technology makes our lives better, safer, and longer, but a strange paradox has occurred in construction. Huge castles and cathedrals, built by people who knew nothing about structural engineering or chemistry, defy time, while our concrete boxes require major repairs after just one generation. The secret lies not in the magic of ancient craftsmen, but in a fundamental difference in the approach to materials, which we have lost in our pursuit of speed. Today we will examine how primitive lime is smarter than high-tech cement and why stone and wood can last forever. Watch the video to the end and you will learn how ordinary rain, which destroys modern houses, was used in the Middle Ages to heal walls. What if I told you that everything you believed about the strength of concrete is not true? We are used to thinking that a wall must be monolithic, rigid, and completely airtight so that it does not let in water or cold. Modern cement creates exactly this kind of structure. It turns into artificial stone that tightly binds bricks or blocks together. However, this rigidity becomes the main problem for a building at the first signs of ground movement or temperature changes. Medieval walls were built on a completely different principle, which may seem like a mistake to a modern engineer. They were not rigid monoliths, but rather flexible structures capable of moving with the ground. The stones in such walls were not glued together tightly, but lay in a soft bed of lime mortar. The secret to the durability of ancient walls lies precisely in this binding material, which is radically different from modern cement. Lime mortar never becomes completely stone, retaining microscopic mobility within the masonry for centuries. When a building settles or the ground shakes, the lime joint compresses or deforms slightly, but does not crack. This allows the wall to absorb stress by distributing the load evenly throughout the structure, rather than concentrating it at a single point. Modern cement behaves like glass in such situations. It is too hard to bend and therefore cracks immediately. Water gets inside through this crack and when it freezes, breaks the wall from the inside. But the most amazing property of lime mortar is its ability to self-repair, which we have practically forgotten about. When a micro crack appears in lime masonry, ordinary rainwater penetrates the wall. The water dissolves the particles of free lime inside the masonry and carries them into the void that is formed. Upon contact with air, the dissolved lime turns back into solid calcite, literally healing the wound. This process is similar to how the body heals cuts, and it can continue for hundreds of years. Modern concrete lacks this ability. A crack in it is a death sentence that will only widen over time. This is why medieval buildings have stood for centuries. They constantly renew their structure, using the environment to their advantage. They do not fight nature by trying to create an airtight barrier, but interact with it, allowing moisture and air to pass through. Lime allows the wall to breathe, removing excess moisture to the outside, while cement locks it inside. Moisture trapped in modern walls becomes a breeding ground for mold and causes reinforcement to deteriorate. Ancient craftsmen intuitively understood that water will always find a way and allowed it to escape. We often look at ruins and think that they have been destroyed by time, but many of them have stood in the open air without a roof for hundreds of years. This is only possible because the materials of the wall are in chemical equilibrium with each other. Stone and lime are similar in nature and react in the same way to thermal expansion in summer and contraction in winter. Modern walls often consist of materials with different expansion coefficients, which literally tear each other apart when the seasons change. We create layered cakes of concrete, insulation, and plastic, which age at different rates. Interestingly, modern restorers often make the fatal mistake of trying to reinforce ancient walls with cement. Hard cement blocks moisture and creates areas of tension, causing old bricks to crumble into dust within a couple of years. This is clear evidence that new technologies do not always surpass time-tested methods. We have learned to build quickly and high, but we have forgotten how to build for centuries, losing the secret of the living wall. This makes us wonder what we will leave behind for future generations, apart from mountains of construction waste. We are very interested to hear your point of view. What do you think about returning to old technologies in private construction? Write about it in the comments. Want to know a secret that will change your perception of simple stone laying? It seems that stone is the most durable material in the world, and it doesn't matter how you lay it in a wall. However, medieval masons knew that each cobblestone has its own internal structure, invisible to the untrained eye. Stone is a sedimentary rock that was formed over millions of years, accumulating layer upon layer at the bottom of ancient seas. These layers create natural lines of stress that determine how the stone will withstand load. If the stone is laid incorrectly, it will begin to delaminate and crumble under the weight of the building after just a few decades. The rule was simple but strict. The stone in the wall must lie the same way it lay in the mountain. This is called natural bedding, when the layers of stone are arranged horizontally, perpendicular to the load. In this position, the stone can withstand enormous pressure as the layers press against each other. If the stone is placed on edge, the layers will begin to peel off under the influence of rain and frost, like the pages of an old book. Modern decorators often ignore this rule for the sake of beauty, and their walls begin to peel after a couple of winters. The craftsmen of the past spent a huge amount of time selecting each individual stone, turning it and studying its structure. They read the stone, finding barely noticeable lines of layers to determine its correct orientation. This required not only a keen eye, but also a deep understanding of the nature of the material they were working with. Often, the top and bottom of a block were marked at the quarry immediately after cutting so that the masons would not make a mistake on the wall. An error in the orientation of even one large block could eventually lead to a crack in the entire wall. In addition, there was a strict system of joining that turned a pile of stones into a single monolith. Vertical joints were never allowed to coincide in adjacent rows so that a crack could not run straight down. Long stones, called buttresses, were laid across the wall, connecting the outer and inner sides of the masonry. They acted as giant stone nails, holding the structure together and preventing it from bursting under its own weight. Without these connecting elements, the wall could simply split into two thin crusts and collapse. The corners of the building were always laid out with the largest and strongest blocks, cut with particular care. These cornerstones, or quads, served as anchors for the entire wall, setting the geometry and taking on the main wind loads. It is the corners that are the first to suffer from erosion in the forces of nature, so compromises were unacceptable here. In cheap modern buildings, the corners are often simply joined together without reinforcement, which leads to the appearance of through gaps. The stones were selected not only for their strength, but also for their ability to interact with the mortar. A stone that was too smooth did not provide adhesion, and one that was too porous sucked water out of the mortar too quickly, preventing it from gaining strength. The surface of the stone was often specially treated to create roughness for better contact with the lime. It was a symbiosis of two materials, each supporting and enhancing the properties of the other. The origin of the stone was also taken into account. Local material was always preferred to imported material. Stone quarried in the same area had already been tested by the local climate, winds, and temperature changes. Imported exotic stone might look beautiful, but it could be destroyed by unfamiliar humidity or frost. Today, we often transport marble or granite from the other side of the world without thinking about how it will behave in our latitudes. Interestingly, walls were often made thicker at the base and thinner toward the top, creating a slight inward slope. This not only saved material, but also made the wall more stable by directing the vector of gravity inward. Rain wets such a sloping surface less, flowing off faster and not lingering on the joints. It is simple geometry that prolonged the life of the building for centuries. Each stone in the wall had its place, its function, and its own history of placement. It was not just a construction project, but the assembly of a giant three-dimensional mosaic designed to last forever. Disregard for these rules in modern construction leads to facades crumbling as soon as the warranty expires. But stone is only part of the equation. The next element was alive before it became part of the wall. In the next chapter, you will learn how ordinary wood became stronger than iron. What I am about to show you is banned in 12 countries as an unsafe construction method, but it is what held cathedrals together. I am talking about the use of wood in combination with stone and lime, which today seems to violate all fire safety regulations. Medieval craftsmen knew that properly prepared oak could rival metal in strength without being subject to corrosion. They did not use simply dried boards, but massive logs that had undergone a process of natural preservation. The secret was to use wood that was accustomed to the conditions in which it was to be used. Oak beams used for floors and frames were often soaked in water for years before use. The water washed out the sugars and juices from the wood that normally serve as food for beetles and fungi. After such treatment, the oak became incredibly dense, heavy, and practically petrified when it dried. It was impossible for insects to gnaw through it, and it burned extremely reluctantly, only charring on the outside. Today we dry wood in kilns for a couple of days, leaving it loose and attractive to pests. The uniqueness of oak also lay in its tannin content, which acted as a natural antiseptic. When in contact with lime mortar, oak did not rot like pine or spruce, but underwent a chemical reaction that preserved it. Lime drew moisture out of the wood, creating a dry alkaline environment around the beams in which mold could not survive. This made it possible to embed the ends of the beams directly into the stone walls without fear that they would rot and cause the ceiling to collapse. Craftsmen never used metal nails in critical joints of wooden structures. Iron inside oak inevitably rusted due to the acids contained in the wood, and the rust tore the fibers from the inside. Instead, all joints were made with wooden dowels, oak pegs that were hammered into holes. Over time, these pegs dried out along with the main structure, becoming one with the beams. Such a joint did not weaken over time, but only became tighter. The timing of logging was no less important than the type of tree. Trees were only cut down in winter, when the sap flow in the trunk stopped and the tree was asleep. Winter wood was drier, denser, and cracked less during subsequent drying. Today, trees are cut year-round for the sake of production volume, resulting in low-quality, moisture-saturated material. Interestingly, for special curved structures, such as roof arches or ship ribs, specially curved trees were sought. A master craftsman could spend years looking for an oak tree in the forest with the right bend in its branches in order to use its natural shape. This preserved the integrity of the fibers along the entire length of the piece, making it incredibly strong. Wooden roof structures were assembled on the ground, fitted with jeweler's precision, and only then lifted up. Each beam was marked with a unique sign to take its only place in a complex three-dimensional puzzle. These marks can still be found in the attics of ancient cathedrals, like autographs of long-gone masters. The ventilation of wooden structures was thought out to the smallest detail to avoid stagnant air and dampness. Attic spaces always had dormer windows to ensure a constant draft. Wood must breathe, and as long as it is ventilated, it can serve for 1,000 years without losing its strength. Modern airtight insulation often kills wooden frames faster than open rain. The combination of stone, lime, and stained oak created a composite material of incredible reliability. Stone provided protection from fire and wind, lime regulated humidity, and oak provided elasticity and bending strength. The building functioned as a single organism, where each organ performed its function flawlessly. If you think these technologies are outdated, just give us a like, and we'll continue to reveal the secrets of ancient engineers. Are you ready for the shocking truth about what castles stand on? Today, the construction of any house begins with pouring a concrete slab or strip reinforced with steel. We try to create a rigid platform that will resist soil movement, but nature is always stronger. Medieval builders approached foundations differently. They did not try to overpower the earth, but sought a way to lean on it as naturally as possible. Often, there is no continuous foundation under huge walls as we understand it. The basis for durability was the incredible depth of the foundation and careful preparation of the base. Trenches were dug under the walls until they reached solid, mainland soil or rock. If there was no rock, the bottom of the trench was tamped down with heavy oak beams until the earth became as hard as stone. It was titanic manual labor that took months, but it guaranteed no subsidence in the future. Instead of hard concrete, they used so-called dry foundations made of large boulders. Huge stones were laid in the trench without mortar, carefully fitting them together and filling the voids with rubble. This construction acted as drainage, allowing groundwater to pass through freely. Water did not accumulate under the wall and could not swell the foundation when it froze in winter. An interesting solution was the use of wooden piles in marshy soils, as was done in Venice or St. Petersburg. Thousands of larch or oak trunks were driven into the soft mud until they hit solid ground. Being completely submerged in water without access to oxygen, the wood did not rot but became as hard as iron. Huge palaces stand on these underground forests, which have not moved for hundreds of years. Sometimes, in particularly difficult cases, they even use sheep's wool soaked in fat. It was laid in layers between the foundation stones to create a cushioning pad in case of earthquakes. It sounds like a myth, but archaeologists find remnants of such wool technologies in the foundations of ancient bridges and towers. The wool did not rot when tightly compressed and dampened ground vibrations. The width of the foundation at the bottom was significantly greater than the width of the wall, creating a so-called sole. This distributed the enormous weight of the masonry over a large area of ground, reducing pressure. The stepped narrowing towards the top allowed the load to be transferred smoothly and prevented the edges from chipping. Today, we often save on the width of the foundation, relying on the strength of reinforced concrete, which leads to distortions. Another secret was to let the foundation settle before erecting the walls. The finished foundation could be left for the winter or even for several years so that it could find its place and settle. Only when the ground had completely stopped moving did they begin to erect the walls. Rushing this process was considered a crime against the future building. The apron around the building was made of dense, fatty clay, which acted as a water barrier. The clay did not allow rainwater to pass under the foundation, diverting it away from the walls. It was a cheap and effective solution that worked for centuries without repair. Modern concrete aprons often crack and, on the contrary, direct water directly under the house. The foundation was the invisible but most expensive and labor-intensive part of medieval construction. Craftsmen understood that it would be impossible to correct a mistake in the foundation, so they built in a triple margin of safety. They built as if the building were to stand until the end of time. But the foundation is only protection from below, so how did they deal with the threat from above? In the next chapter, you will learn how medieval architects defeated water without plastic gutters. The main enemy of any building, whether a poor peasant's hut or a majestic cathedral, was and remains the same adversary: water. It works slowly, imperceptibly, but mercilessly. A drop that gets into a crack, stuck in a pore of the stone, or seeping into a masonry joint, turns into ice and tears the material from the inside with a force comparable to a miniature explosion. The ice expands, bursting the stone, creating micro cracks, and then the next portion of water deepens the damage. Over the years, the wall can turn into a leaky jug. Medieval architecture is essentially a huge, complex, and finely tuned machine for managing water. Its collection, distribution, and rapid removal from walls, floors, and foundations. Builders did not have sealants, bitumen films, plastic flashings, or membranes. They worked only with stone, lime, and the laws of gravity. If you look at any Gothic cathedral, you might mistake it for a fantastic creature covered in horns, protrusions, cornices, and stone faces. But this forest of decorative elements is not just decoration for beauty or to intimidate sinners, but a carefully designed engineering network for water drainage. Gargoyles, those monstrous stone creatures with open mouths, were points of discharge for rainwater from roofs and gutters. They threw the streams far away from the facade so that the water would not run down the masonry, soak the mortar, and destroy the foundation. The further away from the wall the water fell, the longer the foundation, the heart of the building, without which it is doomed, remained dry. Each horizontal element on the facade, whether it was a cornice, decorative shelf, ledge, or molding, had a specific function. On the underside of such stones, craftsmen carved a narrow groove, a drip edge. This insignificant, almost invisible groove worked wonders. It caused the drop of moisture to break off downward rather than flow onto the back surface of the stone. Without a drip groove, water, following the forces of surface tension, would envelop the protrusion and flow down to the wall, where it would slowly but surely corrode the surface, soak the joints, and create ideal conditions for moss and mold. Today, for the sake of a clean, minimalist design, architects often forego such details, and walls begin to dampen for decades. In the Middle Ages, the bases of buildings were almost always made of the most durable and water-resistant types of stone: granite, dense sandstone, and sometimes basalt. This lower belt protected the walls from powerful rain splashes, snow slush, meltwater, and dirt, and everything else at ground level. Only higher up, where the spray could no longer reach, did the masonry begin to be made of softer and more porous limestone or brick, which was much better suited for carving and processing, but did not tolerate constant moisture well. This was a clear functional distribution of materials according to the level of exposure to the elements. Modern buildings are often plastered or clad in the same way from the ground to the roof, and it is the lower part of the facade that is the first to be destroyed. Medieval craftsmen foresaw this and did not make such a mistake. The roofs of Gothic buildings are another line of defense against water. They were made with incredibly steep slopes. The steeper the slope, the faster the water rolls down without lingering or being absorbed into the structure. The rafter system allowed the roofs to withstand not only rain, but also heavy winter snowfalls. Slate and tiles were laid in several layers with a large overlap, resembling knightly scale armor. Minimal gaps were left between the tiles so that even strong winds, which often accompanied rain, could not drive moisture under the roof. Flat roofs, so popular today, would have been considered absurd in that era because they retain water, which means they bring destruction closer. Windows, the weak point of any wall, were always recessed deep into the masonry. They were protected by massive stone brows above and sometimes by side projections. Deep slopes not only gave the window expressiveness, but also served as protection from rain. They created a buffer, an area where the flow of water weakened and did not hit the frame. Glass, which was extremely expensive and had low transparency, was often installed only in the richest parts of the building. The rest of the windows were covered with wooden frames or leather and had to be protected from dampness. Even the masonry of the wall was often constructed so that the stones in the upper row slightly overhung the lower ones. This shift, barely noticeable to the eye, created miniature cascades of protrusions. Instead of a continuous stream of water, separate small streams and drops ran down the facade, barely having time to penetrate the masonry. During a downpour, the wall seemed to sparkle with a multitude of water threads, but remained relatively dry. Inside the walls, there were not only air gaps, but also entire ventilation channels. They helped to maintain air circulation and dry the masonry from the inside. If water did break through micro cracks, joints, or simply in the form of condensation, natural draft pulled the moisture out. This system prevented the accumulation of dampness and prevented the growth of fungus and mold. It was a primitive analog of modern ventilation with constant extraction, working solely due to the difference in temperature and pressure. Medieval craftsmen understood a simple truth. Water cannot be defeated, it can only be directed. Their architecture was subject to the principle of moisture control. Every element, from the huge gargoyle to the barely noticeable drip tray, served one purpose: to catch, drain, discharge, and dry. It was a large, continuous protection system that began working with the first rain and did not stop until the last day of the building's existence. But if water was the first and foremost enemy of stone, what about the other task? Retaining heat, so rare in the stone walls of the Middle Ages. The hidden truth that everyone keeps quiet about is that massive stone walls were often hollow inside. More precisely, they were not built of neat blocks throughout their entire thickness, as shown in movies. Ancient walls were an ingenious sandwich consisting of two outer layers of quality stone and an inner layer of rubble. This technique, called Roman masonry, or emplekton, was the key to thermal insulation and economy. The outer layers were laid out of hewn stone or durable brick, creating a beautiful and durable facade. The space between them, which could be a meter or more, was filled with construction debris. Stone chips, broken bricks, pebbles, and plenty of lime mortar were used. This inner part was called the core of the wall. This layered structure worked much better than solid stone. The many voids and heterogeneous materials inside created air pockets that retained heat. Solid stone freezes through very quickly, but this rubbish filling worked like a thermos. In winter, the walls slowly released the heat accumulated during the summer, and in summer they kept the rooms cool. The core of the wall also gave the structure the necessary flexibility and viscosity. If the outer layer was hit by a battering ram or cannonball, the energy of the impact was absorbed by the soft filling. The wall did not crack through like glass, but only dented at the point of impact. This was the principle of composite armor, invented long before tanks. Lime mortar was poured into the rubble in liquid form so that it would seep into all the cracks and voids. This mass set into a single monolith, binding the outer walls tightly together. The result was a structure that was stronger than the sum of its parts. Modern foam block walls lack this internal viscosity and crumble when struck. The thickness of such walls was not a whim, but a necessity for creating thermal inertia. The massive building functioned as a giant heat accumulator, smoothing out daily temperature fluctuations. In such a house, the climate changed very smoothly, which was comfortable for people and beneficial for the preservation of interiors. Today, we try to achieve this effect with thin walls and tons of fiberglass. However, this technology had a huge risk that all craftsmen were aware of. If water got inside the rubble through a bad roof, the wall turned into a swimming pool. The water washed away the lime and, when it froze, swelled the walls, tearing them in half. Therefore, the integrity of the upper protection of the wall was a matter of life and death for the building. Builders often added organic materials such as straw or even manure to the plaster for better bonding. This may seem wild, but proteins and fibers acted as micro-reinforcement. Chemical analyses of old mortars show the presence of the most unexpected additives that improve the properties of the mixture. This technology allowed the use of any readily available material, making construction cheaper and more environmentally friendly. There was no need to transport perfect blocks for the entire thickness of the wall. It was enough to make beautiful crusts. It was a rational approach that combined aesthetics, economy, and engineering calculations. In the next chapter, you will learn why slow work was a guarantee of quality, not laziness. In today's world, time is money, and construction must be completed yesterday. Customers demand that the project be completed in one season, and builders pour concrete floor by floor without interruption. Medieval craftsmen would have been horrified by such speeds, considering them a direct path to disaster. The main secret of the strength of ancient buildings was precisely slow, step-by-step construction, allowing the materials to get used to the load. The construction of a large cathedral or castle could take decades, even centuries. This was not a result of laziness or lack of money. It was a technological necessity. The walls were raised only a few meters per season, after which construction was halted for the winter. The top of the masonry was covered with straw and boards to protect it from snow and left alone. During this time, the heavy stonework had time to settle under its own weight, compacting the mortar in the joints. The lime slowly gained strength as it reacted with the air. If the wall had been built to its full height immediately, the lower layers of mortar would simply have been squeezed out under enormous pressure. The pauses allowed the lower tiers to harden and prepare to accept the new load. The soil under the foundation also compacted gradually, millimeter by millimeter. The building seemed to grow into the ground, finding its equilibrium without sudden distortions. With rapid construction, the soil settles sharply and unevenly, leading to cracks across the entire facade. Ancient buildings settled along with the ground, maintaining their geometry. The slow pace allowed errors to be identified and corrected at an early stage. If a crack or skew appeared somewhere over the winter, the craftsman would see it in the spring and could reinforce the weak spot. It was constant monitoring of the condition of the structure in real time. Modern houses are delivered turnkey immediately, and hidden defects become apparent when the builders are long gone. The change of generations of craftsmen on the same construction site ensured the transfer of knowledge and the preservation of quality. Apprentices grew up on the scaffolding of the cathedral, studying every stone, and became craftsmen who knew the building like the back of their hand. This created a continuous tradition of responsibility for the result. Today, crews change every month, and no one knows what the previous workers did or how they did it. The wood in the structures dried and warped gradually in an open frame. It could be tightened, trimmed, or replaced before it was covered with finishing. In modern houses, raw timber is covered with plasterboard, and when it starts to warp, the walls become wavy. The openness of the process guaranteed the integrity of the structure. The economy of that time was different. Buildings were constructed to last for centuries, for great-grandchildren, rather than for quick resale. Investments in quality were considered the most reliable investments. Slow construction spread the costs over time without requiring huge instant loans. It was the organic growth of a building in line with the community's capabilities. Even the preparation of the lime itself took time. It was slaked in pits for years. It was believed that good lime should be aged for at least 3 years, and for particularly important works, for decades. The longer the lime lay in the pit, the more plastic and durable the mortar became. Today we use dry mixes from a bag that are only a couple of months old. Patience was the architect's main tool, more important than a plumb line or a level. Understanding that nature needs time to complete chemical and physical processes was the basis of craftsmanship. We try to cheat time with chemical accelerators, but you can't cheat physics. We pay for speed with the durability of our homes. We are used to seeing medieval castles as gloomy masses of gray stone, but this is a historical mistake. During their heyday, most stone buildings shone white, covered with a thick layer of lime whitewash. This was not just paint for beauty, but an essential protective layer, a kind of skin for the building. Whitewash, or lime plaster, served as a sacrificial layer, taking the first blow from the elements. The lime applied to the stone filled all the micro cracks, pores, and irregularities in the masonry. It created a smooth surface over which water rolled off, unable to cling to and penetrate inside. It was a cheap and effective waterproofing solution that any apprentice could renew. Without this protection, porous stone and joints began to crumble from wind and rain. Moreover, lime whitewash had powerful antiseptic properties. The alkaline environment killed the spores of moss, lichen, and mold, which destroy stone with their acids. The white walls were sterile, which was important in the unsanitary conditions of the Middle Ages. As soon as the castle stopped being whitewashed, it began to turn green and decay. The white color also helped regulate the building's temperature by reflecting the sun's rays. In summer, the walls heated up less, which reduced the thermal expansion of the stone and the load on the joints. The building breathed less from temperature changes, maintaining the stability of the structure. It was a simple physical principle of protection against overheating. Renewing the whitewash was a regular ritual, similar to spring cleaning. Every year or two, the walls were covered with a fresh coat, covering new cracks and damage. It was a constant preventive measure that prevented minor problems from turning into a disaster. We, on the other hand, wait decades for major repairs until the plaster starts falling on our heads. Interestingly, animal fats, casein from cottage cheese, or linseed oil were often added to whitewash. These additives made the coating water-repellent and more durable, almost like modern facade paint. But unlike paint, lime plaster did not create a film, allowing the wall to breathe. Modern acrylic paints often trap moisture in the wall, causing the coating to peel off. Interior walls were also whitewashed with lime, which created a healthy microclimate in the rooms. Lime absorbed excess moisture from the air and released it back when it became dry. It was a natural climate control system that prevented dampness. Today, we combat condensation and stuffiness with expensive ventilation systems. When we look at the bare stones of ancient ruins, we see the skeleton of a building stripped of its protective skin. The romance of wild stone is a 19th century invention. To medieval people, a bare wall looked unfinished or abandoned. Protecting the surface was as important as the strength of the foundation. A culture of constant care and minor repairs was part of life. Owners knew that a building was alive as long as it was cared for. Today, we build on the principle of build and forget, hoping for eternal materials that do not exist. Neglecting regular maintenance kills modern buildings faster than bad concrete. Whitewashing was a simple, cheap, but ingenious solution to many problems at once. It protected, disinfected, regulated temperature, and decorated. Abandoning this simple technology in favor of expensive polymers has deprived our homes of their natural protection. It is important to understand one thing. We admire ancient buildings, but we only see the champions. This is a classic survivor's error. Only those buildings that were made perfectly have survived to this day. Thousands of crooked, poorly constructed, and cheap medieval houses collapsed and disappeared without a trace hundreds of years ago. We compare the best examples of the past with the average quality of the present, which is not entirely fair. The Middle Ages were also full of hack builders, thieving contractors, and collapsed walls. The chronicles are full of stories about towers that fell immediately after construction and cathedrals whose arches collapsed. Natural selection in architecture was cruel. Everything weak was mercilessly destroyed by time. Only those buildings remained where craftsmanship, quality materials, and a good location came together. However, even taking this into account, the survival rate of stone buildings is striking. Those buildings that passed the test of the first century moved into the category of eternal. They reached a state of static equilibrium when all shrinkage ended and the structure froze. Modern buildings are often designed with a service life of 50 to 100 years, after which they are supposed to be demolished. We build temporary housing from temporary materials because the world is changing too fast. Medieval people built houses that their great-grandchildren would live in. The difference in planning horizons dictates the difference in technologies. We cannot afford to build walls a meter thick because land is too expensive and we need space now. But the problem is not only economic, but also one of material compatibility. Ancient buildings consisted of 3 to 4 components: stone, wood, lime, and iron. A modern house is like Mendeleev's periodic table: foam, films, sealants, plastic, drywall. These materials have different lifespans and often chemically conflict with each other, destroying each other at points of contact. The complexity of modern systems makes them vulnerable. The more complex the wall structure, the greater the likelihood of installation errors. One poorly glued vapor barrier can rot a frame house in 5 years. A massive stone wall forgives minor mistakes, but a modern high-tech wall does not. We have also lost the ability to repair. To repair an old wall, you need to remove the stone and lay a new one on mortar. To repair a modern facade, you often need to strip off the entire cladding and replace the insulation entirely. Our houses have become disposable gadgets. It is easier to buy a new one than to repair an old one. But even among the ruins of the past, we can find lessons for the future. The principles of physics that hold cathedrals together have not gone anywhere. Gravity, humidity, and temperature work the same way they did 500 years ago. Ignoring these laws for the sake of fashion or economy always leads to one result: cracks. We should not blindly copy the past, but we must understand why it works. By dismissing centuries of experience as outdated, we make the mistake of overconfidence. Technology should help materials work, not force them to do what they are not designed to do. Understanding that not everything old was perfect helps us to soberly assess the real achievements of the masters. They were not magicians, they were observers who learned from their mistakes. And the mistakes they corrected turned into the castles we admire today. Today we live in a world of airtight thermoses. We seal our homes with polystyrene, install plastic windows, and seal all the cracks with foam in pursuit of energy efficiency. But the paradox is that in our quest to conserve heat, we have created the perfect conditions for the destruction of walls. Modern materials cannot remove moisture. They accumulate it. The dew point, the place where vapor turns into water, is often inside the wall or insulation, where moisture begins its destructive work. Cement, which has become the basis of all construction, has given us speed and compressive strength, but has taken away flexibility. The reinforced concrete frame is rigid, while the block wall filling lives its own life. Microcracks inevitably appear at the joints, through which cold and dampness penetrate. We fight this with new layers of chemicals, creating a vicious circle of problems and solutions. The service life of modern insulation is 30-50 years. This means that in half a century, our houses will turn into pumpkins. The insulation will crumble, the films will dry out, and the house will become cold and damp. To save it, it will need to be dismantled to its foundations. This is planned obsolescence on an architectural scale. Ancient walls were single-layered and understandable. Their condition could be assessed visually. If the stone crumbles, replace it. Modern walls hide their problems under siding and drywall until the last moment. By the time we notice the problem, it is often too late. Mold has eaten away at the frame. We have forgotten about thermal inertia. Lightweight frame houses heat up quickly, but cool down just as quickly, requiring constant heating or air conditioning. Massive stone walls acted as a battery, smoothing out peaks in energy consumption. We have become dependent on active life support systems, while old houses work passively. It may seem impossible to go back, but that is not the case. Modern architects are rediscovering hand-molded bricks, lime plasters, and natural wood. Eco-friendly construction, or green architecture, largely repeats the principles of the Middle Ages, but at a new level of knowledge. We are learning to combine the durability of stone with modern comfort. The use of porous ceramics, which breathe like brick but retain heat like foam, is a step in the right direction. We are beginning to understand that a house should not be a barrier to nature, but a filter that can interact with it. Perhaps in 500 years, archaeologists will find the foundations of our skyscrapers and be surprised by the amount of rusty rebar and plastic. And next to them will stand the same medieval cathedrals, only slightly aged. It will be a silent reproach to our consumerist civilization. The history of architecture is a spiral. We have moved from stone to concrete and glass, but perhaps it is time to bring back some living materials into construction. After all, a house is not just a machine for living in, it is a person's third skin. We have pieced together the secrets of the ancient masters and realized that their technologies were not primitive, but ingeniously simple. They built in harmony with nature, time, and physics rather than against them. Their walls breathed, healed themselves, and became stronger with age. Modern technologies have given us comfort and speed, but they have taken away the feeling of eternity. Perhaps the truth lies somewhere in between, in a combination of the wisdom of our ancestors and the possibilities of the present. What topics would you like to see in the next videos? Perhaps the secrets of heating huge castles or the truth about medieval hygiene? Share your ideas in the comments and don't forget to subscribe to the channel so you don't miss out on new historical investigations.